For the next talk, we have John Hershey. So John Hershey is a researcher at Google Research in Cambridge, Massachusetts, where he leads a research team in the area of speech and audio machine perception. Prior to Google, he spent several years in Merle and a few years in IBM's Watson Research Center in New York. He obtained his PhD from UCSD. He will give a talk on parsing nature at its seams, unsupervised and audiovisual sound separation.
Hi, everybody. Can you hear me?
Yeah.
Okay, great. And I haven't tested the audio yet, but I'll just come to that when we get to it. Yeah, so very happy to be here. I'll be talking about unsupervised and audiovisual sound separation, and this is a collaboration with a large number of people, two of which are there, and I hope you got a chance to talk to them or check out their poster at the poster session. That's Scott Wisdom and Ephemios Tsinis. One sec while okay. So here's an outline of the talk. First, I'm just going to talk about separation problems in general and how the degree to which you solve more open problems leads to user interface problems that need to be solved. There's sort of a trade-off between the constraints of the problem and the user interface aspects. And then I'll talk about one direction that tries to solve this problem, which is distance-based separation, which relates to the spatial aspects that people are touching on in the rest of the talks. Then I'll transition to unsupervised separation learning and show how that's used for another approach to solving this user interface problem in the general case, which is our audiovisual separation. So, as you all know, sound separation involves taking in a mixture of sounds, running it through a model that produces estimates of the individual sounds that are in the mixture, whether they're speech, non-speech, or what have you, music. One thing that we've noticed is that, we started with very constrained problems where, for example, in speech denoising or enhancement, you're separating speech from non-speech. So it's a very constrained problem. It's easy to kind of train a model for that problem. But there's this assumption that, you only want the speech, that all of the speech is relevant, and that none of the background sounds are relevant. So like this leads to situations, for example, with video conferencing where people try to clap and that gets blocked by the denoising. So it's a type of system that works well, but there are disadvantages to being so constrained. In speech separation, you're separating all the speakers from each other. And the problem there is that, there may be some speakers that actually you don't want to preserve. So once you've separated things, you have to decide which speakers are relevant. For example, if you're out in a cafe situation, then, separating the individual speakers at your table might be worthwhile and to preserve them, but you maybe want to block the other ones. And so how do you determine which ones the user wants to hear? And then finally, when you completely open up to what we call universal sound separation, or you can say open domain sound separation, where the task is to separate any sound from any other in the mixture, then you really have an even harder problem to decide which sounds are relevant. And the relevance often depends on the context. What is the goal of the user of the system? What are they trying to achieve? So some of the work that I'm presenting deals with these things in different ways. So in supervised speech denoising, just to give a picture of what is commonly done, usually we assume that we have isolated sources for training. We have clean speech and we have non-speech sources, and then we can mix them together, form a mixture, and use a separation model to produce estimates of them. And then we train the separation model by ensuring that the output that is supposed to be speech matches the speech, and the output that is supposed to be non-speech matches the non-speech references. So this type of training modeling has been going on for a long time. For distance-based separation, we want to do that distinction between what's preserved and what's rejected in a different way. This idea was actually inspired by my dad. I took him out to dinner, and he asked me, why can't I get a hearing aid that just preserves the sounds that are at my table and blocks all the sounds from other people in the restaurant or other things in the restaurant. And one aspect of that is you may also want to preserve the non-speech sounds too. So, if there's a toast and the glasses are clinking, or you drop your keys or something, as a hearing impaired person, you don't want to live in a world that is where you're deaf to non-speech sounds, right? You want to hear all of the sounds, but the relevant ones. And that could be context dependent too. So if you're in a talk, maybe you want to hear the faraway sounds and not the near sounds. So can we, my answer was, I don't know. Why can't we do this? And so we set out to sort of test that idea. So it's exactly the same paradigm as for denoising, but now instead of having speech and non-speech, we have nearby sounds and faraway sounds. So we mix those together and train the system to separate those two categories of things. So the advantage of this is that it gives a very simple, intuitive separation criterion, for a hearing aid or something like that. It's a very easy user interface. You can imagine having maybe some controls on it to switch whether you're listening to far or near, or how far away constitutes far, and it can preserve the relevant non-speech, which speech enhancement systems can't do. And there was a kind of idea with this that maybe this could allow for more efficient separation systems, since if you think about it, the distance cues have to do with superficial aspects of the sound, right? It's not the sound class and category itself, so it's not the spectral pattern of the sound in the sense of identifying what type of sound it is, which is the case for speech versus non-speech separation. But instead, it's really about something that is sort of painted onto the sound. So you can imagine like an analogy with vision, if you're separating things that are colored in a particular way from things that are not colored, then you don't have to actually recognize the objects. You're just sort of detecting the superficial coloring. So there was an idea that maybe this could lead to more efficient models. And we haven't fully probed that part of the idea, but we hope someone will. So to do this problem, we had to do some simulation. Maybe not quite as advanced as what Dinesh was talking about, but we distributed sound source locations, in artificially simulated rooms. And, we had a particular density that we chose to make the distribution over the distance from the microphone roughly uniform. So this is the distribution that we ended up with because, well, you have edge effects as you get close to the walls. You don't want to have sources that are running into the walls. And this picture is kind of blurring over the distinction that there are actually many different room shapes. We have different wall materials. These are all just simple rectangular rooms. Like the thought of simulating the complex geometry the way Dinesh did was sort of beyond our capability at that point. So we did show, though, that even like we could train a model with these simple sort of training criteria to separate a number of sources near or far. We just use speech in this case. We had a sort of a source presence probability for controlling the distribution over the number of sources. So the number of sources is unknown, but it's generated by pre-generating a fixed number of locations per room, and then having a presence probability for each of those to generate a distribution over the number of sources that are active. And in training, that presence probability was 50%. In eval, it was 1, but we had a variable number of sources. So, and those are divided out here in the table. So you can see that as we got more and more sources, the improvement in the signal to distortion ratio, which is what we're measuring here, it goes down for nearby sources. Nearby sources are sort of harder to show an improvement because they're already at higher SDR to begin with because they're closer to the microphone. And the far ones show more improvement because they're further away and they're more masked by the nearby speech. I don't know if it's anything about the innate qualities of near and far sources that makes this difference. I think it's more just about the starting SNR. And I'll give you a demo of that. Cappy Patterson, the person who did most of the work here, made this nice demo by recording in her apartment with one nearby speaker sitting on the couch there, and a far speaker sitting on the chair across the room, and a phone was used to do the recording, also on the same couch as the near speaker. So I'll play the mixture first here.
I am a close by person, and I'm wondering if my voice will be filtered out.
Did everybody hear that?
Yes.
Great. So here's the far speaker.
Hello, I'm a faraway person, and I'm wondering if my voice will be filtered out.
So that's the estimated far speaker, single microphone. So the only possible cue here is the spatial difference. This is all speaker independent. Here's the near speaker.
I am a close by person, and I'm wondering if my voice will be filtered out.
So this answered that question. Yes, it is possible to just use distance and the distance-related cues, at least with our artificially simulated data, training data, to solve this problem, and it can work in real case, real life examples, as this demo is here. And we suspected for a long time that this cue was there and is used by other separation methods that we use in different kind of tasks where we don't explicitly tell it to use that cue, but this just confirmed that cue is something that can almost solve the problem in some cases. So now when we go to separating things of the same type, a methodology that's been adopted over the years is permutation invariant training. In that case, we don't have an a priori criteria like distance or the class of the source to use to distinguish what the order the outputs should be in. So instead, we let the model output the source's estimates in any order, and then we look at their correspondence to the original reference sources and permute the order appropriately so it matches the reference sources, and then compute our loss from there. So it's a very simple method to deal with that permutation problem. And this type of approach has been applied to some very narrow tasks like separating two speakers from each other. And a lot of progress has been made over the years. So when the task was first introduced, actually by my lab at Merle back in 2015, 2016, a lot of progress was made over time. What we observed is somewhere around the middle of this path upward here, that the models that were being proposed stopped really being generalizable to other tasks. So when we try them on other tasks, like enhancement, they didn't actually show particular benefits. So there's the danger that we always have of being overtuned to a particular data set or a particular problem. And our direction instead has been to go in the other direction, to kind of like open up to all of the audio separation tasks. But to do that, we found out that supervised training is not enough. The benefit of supervised training is that you have artificially mixed data, which provides a reference source for solving the problem on a particular example, and so that's a very strong learning signal. The problem is it's very difficult to match the distribution of acoustic effects and sound types and their composition, how overlapping they are, what sounds occur together, and so on, in real data when you're doing synthetic data. And as Dinesh showed, it's actually a very complicated problem. There are a lot of acoustic effects, that one might want to model diffraction, and then there's the problem of the irregular geometry and the materials, and the distribution of those in your target domain. How do you match that so that your training data matches your test data? So that's very difficult, and I appreciate all of the progress towards having better simulators and better data sets that cover a lot of different geometries and materials and so forth. This is all very, very helpful. The other aspect is just the reliance on isolated sources that supervised training entails. Like, this really limits the amount of training data that we can gather. I mean, some types of training data we have plenty, like speech, we have a lot of isolated sources. But when you get into all the other types of data, some of them are almost never recorded in isolation. And in other cases, there's just a very long tail of types of sounds that it may be hard to find in isolated sources. And in contrast, there's a huge, huge bounty of mixture data. Practically all sound that's recorded is, can be considered mixture data. And we'd like to be able to use that. So the disadvantage with unsupervised training then is that we don't have those isolated sources, but we can use that practically unlimited open domain training data where we don't have to curate anything or very much. We just have to grab as much data as we can and start training on it. And then if we have a particular application domain where we want things to work and we want to match that distribution, we can just use the application data itself. So here's how our current method of doing that works. So this is a method that we found works well. It's a little bit less complicated than other avenues towards unsupervised sound separation learning, but we think that it's worth exploring other avenues too. So, but here's how this works. So we take our mixtures, and we take two at a time, and we mix them together to create a kind of like artificial super mixture. We call it a mixture of mixtures. And we run that through our separation model. And then it sort of works like a generalization of permutation and variant training. You have then a number of sources that are produced. Some may be silent, some may contain sounds. And then for each estimated source, we decide which mixture it best helps reconstruct. So we have an assignment from each estimated source to one of the mixtures, and only one. And then we mix all the sources together that are assigned to mixture one and use reconstruction loss for mixture one. We mix all the sources together that are assigned to mixture two and have a reconstruction loss there. So that very simple process is sort of like all that is involved in mixture and variant training. You can use any type of model. You can combine mixture and variant training with any other type of unsupervised losses or estimation techniques. So we found this to be very useful, and we've used it for a lot of different tasks. So the first one was just trying out this universal separation idea. Our initial take on this was to try to use fixed training data where we have isolated sources, but we found that very limiting, and it turned out that we could do better by training on larger databases of mixtures. We looked at domains where there are no isolated source data. So for example, in bioacoustics, often all you have are field recordings, and the subjects of study don't come into the studio to record their voices independently. So I'll show an example of that next. We've also used it to adapt supervised models on real domain data. And this can be done using federated learning or privacy-preserving learning, so that no human has to look at the actual domain data. It just is fed to the algorithm to update the model and get a supervised model to work better on the real domain data. And this can be done with multiple channels too, and something that we're working on. And then we found this to be a kind of ideal basis for doing audiovisual separation. So at the end, I'll switch to talking about Audioscope, which is our audiovisual separation model. So here's first an example with bird call identification, where, as I said, you have field recordings, but they always have overlapping sounds. There are no natural bird calls that are recorded in isolation. And that makes labeling them and classifying them difficult, and obviously it makes it hard to just hear individual bird calls. So we trained our separation, just a generic separation model on these unlabeled field recordings, and this is kind of what we get. So first you're going to hear the entire mixture, and you see the spectrogram here. And then you'll hear each of the sources that was identified by the separation model, and the corresponding bird that produced that source will be highlighted. So let me play it. Oops, let's see what happened there. That's bird number 1. Bird 2. Right. So, not being a birder, I wouldn't have been able to distinguish those either looking at the spectrogram or hearing them, and I might not have even known how many birds were there, let alone what type they are. But so this unsupervised learning can be powerful in its ability to do that. The next demo is an even harder example in some sense, because the bird calls are overlapping in time and frequency, and so it's subtle. You can see in the spectrogram that there are 2 different things going on there, so it's not like it's completely unclear, but I think it's remarkable that the model is able to sort of pick these out. So let me play that. Oops, not sure why that's happening. So there you go. Yeah. So also, this is all with a single microphone, of course, and stay tuned for the multi-channel version of this in upcoming publications. So now I want to switch over to audiovisual on-screen separation. So this is another, it's a methodology that serves as a user interface element. It's doing audiovisual separation, and the importance of that is that using what the user is focusing on to trigger the separation, the decision about what sources should be separated, solves that user interface problem in a kind of intuitive way. So here you have a bunch of sounds in the environment. There's some wind noise and a couple people talking and a dog barking. Now the user takes their camera and points it at the one person talking and the dog. But the microphone, of course, still captures everything. And so this goes into the model, and the model then uses the combination of the 2 things to separate the on-screen estimates of the dog and the first person talking from the off-screen estimates. So, a conventional way to do this would have been, use supervised training and find videos with only on-screen sounds and combine those with other sounds and then train to separate those. The problem is it's practically impossible to gather enough supervised data. Even if you filter existing data to find videos where there's only on-screen sounds, you end up with far less data than you would otherwise be able to obtain. And it's very expensive to do that human labeling. So we realized early in this that we actually just had to use unsupervised separation. Fortunately, we had the Mixit algorithm available, so we were able to do that. I just want to highlight some differences between the audioscope work and other audiovisual separation work. First of all, some other work has used object detection systems where you have like pre-trained visual object detectors, and you use that to sort of decide where to focus for separation. We don't do that here, and we think it's an advantage because then the system can learn what's important in the image, what's likely to be making a sound, regardless of the sort of object type, and it can also learn sort of the long tail of different objects. Another thing is that we allow, partly because of that, we allow separation of a large number of classes of sound, and also we can handle a variable number of sounds, where the number of sounds is unknown. And more generally, we're sort of robust when training on in the wild videos with both on-screen sounds and off-screen sounds. We can then apply the system to unconstrained situations. It doesn't have to be someone facing the camera. It doesn't have to be a case where you can see exactly that the object is making the sound. It can handle cases where that has to be inferred. So here's the general architecture. So this is a separation first type of system. Because we can actually pre-train a model to do well at separation, we start with this audio separation model. So we take an input video training time and mix it with some other audio. Now that input video may have off-screen sounds as well, so it's not a cut and dried supervised problem. And the audio separation network then produces some estimated sounds. To figure out which sound is on screen, we have an audio embedding network that takes those sounds and produces an embedding for each sound over time. And the image is also analyzed with an embedding network that produces an embedding for each location in the video over time. So we take those streams of embeddings, we use audio-visual attention to sort of combine the information and implicitly, figure out which source is coming from which location in the video so that we can classify, is that source coming from on screen or not? Once we have probabilities for whether each source is on screen, we can create an on-screen estimate by combining the probabilities with the original separated signals. For example, just multiplying the probability of it being on screen by the signal itself, and we get an estimate. But for training, the difficult part is, what are the labels for a source being on screen? So from our mixture invariant training, we have these assignments between the sources and the mixture, the input mixture that they best reconstruct. So those form pseudo labels that we can use. The problem is, like I said, the input video soundtrack might have some off-screen sounds. So we can't do this in a tightly constrained way. It has to be sort of like multiple instance learning. We allow the system to classify some things as off-screen while forcing it to assign at least one thing to on-screen. Over the years, we've kind of made some improvements with this. The original version operated at 1 frame per second and had a much less complex audiovisual attention module. We improved the audiovisual attention model and moved it up to 16 frames per second, and it got some nice improvements there. That paper's worth taking a look at. And so here's a demo of how it works. So this is going to be, again, like 2 clips, one the mixer and then one the processed video. And some of these are a bit subtle because these are real videos. So listen to the first part and try to hear what part of the sound should be removed or doesn't seem to be coming from anything that's on screen. And then listen to the second one to see how well it succeeded. And what you should hear is that in different contexts, different things are removed depending on what's on screen.
Mother program is Louisiana program is mother program is Louisiana.
Where is it?
Penny.
Where is it?
Penny.
Adquirido do mundo.
Okay, so I mean, what makes me so excited about this work is that it's handling all these very ambiguous situations where you don't have, frontal-facing faces, but we can still infer where the sound is probably coming from, and so can the model in many cases. And it has the ability, like in that last example with the car, of actually separating one type of noise from another type of noise, where like the extra rattle that the car has is sort of deemed not fitting with the situation because you're just seeing an ordinary car, so there's no sort of evidence that it should be this extra weird independent rattle going on. So it's just the flexibility of this type of system and the ability to handle ambiguity, I think, are its hallmarks. So that's all I've got. I talked about how separation problems have different user interface problems, and the more general you go with separation, sort of the more problems you may have to solve, but then how different tasks can kind of address that, and also along the way that unsupervised separation learning is sort of an essential way to learn how to scale our training to handle a much wider set of problems. So thanks very much.
Any questions?
Hi. So for the distance learning separation, did you or what's your experience with many speakers? Because you actually have shown 2 speakers, and one is predominant, the other one is not. So I guess it's some sort of binary thing. But if you have, like, let's say 4 speakers and they are in similar or not the same distance, but how does it perform in that situation?
Yeah, so we went up to 4 speakers in our experiments, and so in the slide that I showed, you can see that the more speakers there are in either near or far, the worse the performance is. So the SDR goes down by the time you get to 4. That may also be because there are fewer cases where there's 4 speakers in each source or in one source or versus the other. So I think that remains to be explored. How far can we take this? The goal, of course, is that it shouldn't really matter how many speakers they are, because their sort of superficial reverberation characteristics should be roughly the same in each category. But I know that's an oversimplification.
Okay, thank you very much.
Hello, John. This is Tuomas. Thanks for a very nice talk. So I have a question about also about the distance-based source separation. So there you had the threshold at 1.5 meters. So obviously, if you have sources very close to the threshold, let's say one that is above 1 centimeter above and one is below, the difference in the acoustic cues is very difficult, which makes the tasks very difficult in that sense. And okay, I guess you were doing offline processing, so maybe that's not a problem, but then if you consider, for example, real-time implementations at some point later and moving sources, then this becomes some issue. So do you have any idea how to make this kind of system behave kind of smoothly when there are sources kind of close to this kind of threshold or decision boundary?
Yeah, thanks a lot, Thomas. That's a very good question. Yeah, I mean, this is sort of, it's something that we tried to deal with by experimenting with different margins for classifying things as near or far. But in the end, the system is always going to have to make some kind of decision or fade things from one case to the other. And I guess one idea we had was that this should be actually a user parameter that they can adjust. Sort of setting the threshold. We didn't train a model that way so that you could adjust it on the fly, but that was kind of one of our goals. So like the using distance itself is kind of a funny thing to do, because the relationship between the way the reverberation changes as a function of distance, that changes as a function of the environment. So in more reverberant environments versus less reverberant environments, the difference in, we think the main Q is the direct to reverberant response, ratio. And so that would be a different function if the environment is different. Although the loudness itself might be a more stable function of distance. So we think that in any case, it's going to be necessary for a user, if someone's using this as hearing aid, it's going to be necessary for them to be able to adjust that threshold. And yeah, I mean, I think it would be neat to be able to sort of track the sound. So if it just goes out of bounds and comes back in, then it could just track over time. But that's obviously a little more complicated.
Any more questions? All right, if not, let's thank John again.
I think there was one question on the chat, actually.
Or,
Sorry.
yeah, go ahead.
So the question was how to produce the demo with the mixed audio and the spectrogram covered with others. I think what you mean is like when we do the separation, I'm highlighting different parts of the spectrum depending on which separated source we're looking at. So basically what you're seeing is a composite spectrogram at the end combined with all the combined estimates where we're highlighting one, with the color according to the estimated spectrogram. So we see the mixture spectrogram, but the highlighting in different colors comes from this spectrogram of the estimated sources, if that makes any sense. So all the data is real there, but we just have the estimated sources that we're using to color the mixture spectrum.
Thank you.